Hi, everyone. My name is Eugene Bagdasaryan. I'm a PhD student at Cornell Tech in New York, and my collaborators, Andreas and Ichin, and my advisors is Deborah Estrin and Vitaly Shmatikov. This is work done for privacy and security in federated learning, and the title of the work is How to Backdoor Federated Learning. I'm really happy to be here at DataFest, and let's move on. So federated learning is very interesting concept, but let's just start with a very simple example, a predictive keyboard. All of us know how this technology is very popular. It is it's used in Google search. It's used in this keyboards where what we type, and then we get these predictions on what the next word would be. And this is a very useful feature, but also it's very sensitive and it can contain sensitive information, especially of what we type on our keyboards. Traditionally, the way this type of applications were trained, so there is a machine learning model that tries to do this prediction, and in this large-scale machine learning model, the model would reside on a company side, in a big data center, and then they would get, this model would be trained on data from all the users. So all the users would have to send their data to the data center and then train the model together. And in fact, it's not just few users, it's basically everyone who types anything on their phones or in the search bars would be sending the data to the data center. This kind of results in a problem with privacy, since the data center needs to have more security and trust from the users to not compromise their data. And a recent concept called federated learning was proposed to keep the data locally on the user phones and only transfer models between the data center and the users. So what initially happens, it's a very simple concept introduced in around 3 years ago by Google, where the model is first, kind of initial model first distributed to a subset of users. They train this model locally on their data and then send the model back to the data center. And then this number of models are aggregated and averaged together, and it becomes a new global model. And then the same process repeats. The model is again sent to another group of users. Then they train on their own data and then send it back. So what happens is basically we can cover, with this process, we can cover all the users, not at the same time, but by selecting subgroups. And the reason why we want to select just the subgroups, there are multiple reasons for it. One is that if we have millions of users participating, we cannot always expect them to be online. And also for the convergence reasons, if we get models from different users and there are thousands and millions of models, it could happen when we average, it might, all the subdates from the users might just cancel out. So we still want to have a smaller subset. It's very similar to batch size concept in the traditional machine learning. The overall features that federated learning has are really kind of destined for success in real world, because the federated learning supports non-ID data. Basically, everyone who has the different data can participate in this training, and it doesn't really rely on it doesn't rely on the data being similar across devices or equally distributed or IID. And similarly, some users might have more or less data, which is as well a huge assumption that in many cases smartphones cannot store a lot of data. Some smart phones can, and so on. It also supports this massively distributed. As I said, that you can select a subset of users each time, and then after some iterations, some number of rounds, you can actually cover most of the users. And it supports millions of smartphones, which Google was showing that it actually runs on their production devices. And it also supports this smartphones joining and leaving the training at so it's like they can't join this round of training and then they can leave it, but still when the results are averaged, it will be all fine. So there are no significant problems and overhead with this technology. And the biggest feature that federated learning provides is that the users only share the model, not the text that they type, and they only train the model locally. So the model trains on the local data, and the real data is not sent to data centers. There are a few really great examples of interest from the academia, from industry in federated learning. First of all, in this recent keynote of 2019, CEO of Google, Sundar, presented federated learning as a future of Google personalization and AI, where they don't really want to get access to user data, and they will rely on training the models locally. And also Google has created a really funny comic on how federated learning works. So you're all welcome to try it out. Somebody even calls federated learning as a new dawn of AI. And there are a lot of startups that try to kind of put federated learning into life. And the main premise is that Bitcoin price dropped, but a lot of people bought GPUs to mine Bitcoins like a few years ago. And this is a great environment to run federated learning. So there are some startups that propose to for users who own GPUs to train their models locally, and then only send the models and kind of create a marketplace for trained federated models. Some very simple example of how federated learning works. There are two parts of federated learning, kind of server side and client side, or like device side. On the server side, as I said, that you create a global model, and then you run multiple rounds where you select a subset of users, some subset M from all the users. And then for kind of each user, usually done in parallel, you send the global model to them, and then they compute the update and return this update. You accumulate the update, and then you apply this update to the model and kind of create a new global model as you go. And on the client side, it is as well very simple machine learning routine where you get this global model, you run some number of local epochs on your data. And it's important that this training on local data is very prone to overfitting, because you usually don't have enough data to train on. So you don't really want to run too many epochs locally. But then you run this model with some learning rate and batch size, and then you basically send a difference or like update with the global model. In some sense, it could be seen as a gradient to in the normal training, but in fact, it's just a difference from the global model. And there is an interesting area of research where they try to, instead of just averaging, as what we show here, to use other types of aggregation methods or optimization methods based on Adam and momentum to improve the performance. It's a very exciting area of work right now. However, what important things that we see here is that before, when I was talking about kind of like centralized training, where all the users would send the real data to the server, in this case, you only send the model. And it results in a very interesting side effect where before the server or the company could have just looked at the data and see if the data is good or bad. In this case, what you send is a model. And in fact, it's just a bunch of numbers, just matrices. And it's a little bit less clear what this model does compared to just looking at the raw data. So we have evaluated this idea of users participating in federated learning, but one of the participants is compromised. What this participant does, it tries to introduce a specific adversarial feature called a backdoor into their model, into this device's model, but also to a global model, so that this behavior will be distributed to all other participants, and maybe will apply it in some other scenarios as well. But there are some challenges, right? So because there are all other participants, it's not that this attacker who compromises the phone. And it's in this case, it's very simple, right? So there are like a lot of examples of rooted Android phones or iOS phones where the participants, where you can compromise the code of the platforms. Also now it is much more secure than it used to be. But on the other hand, there are all other open source frameworks like OpenMind and others. I think there is a FedML frameworks, and they usually propose an open source version of their code. So it could happen that if I take just open source, that some adversary takes this open source code and might do something to introduce this backdoor. Let's talk about this type of this attack, of the backdoor attacks. In some scenario, it's a poisoning attack where you want to compromise data, but it can be even stronger than just poisoning. You can compromise the training as well. And the feature of this attack is that there is a certain element on the inside the input. So if we look at this two images, two images of 7, and the normal model will always label it as 7. The first image doesn't have any artifacts, and the right image has this white artifact in the bottom right. The backdoored model, if it sees a certain feature, and in this case the feature is this white pixel over here, the backdoor model, when it sees this feature, it will mislabel the example. Also, it's still the image 7 for all of us. It will mislabel it. That's a little bit similar to what the adversarial examples are trying to achieve, and or universal adversarial examples that they're trying to achieve. But there is a slight difference here. And the first is in adversarial examples or universal adversarial examples, you don't really control the type of this feature. And in the so like in adversarial examples, you have to run some attack, and then you get this pattern or noisy patterns that you apply to the image. It usually requires to be kind of the adversary to have access at the input time. So somebody needs to come and, in adversarial examples case, modify the picture, add some noise. In the backdoor case, the feature could be just a physical key. Like in this case, it's just type of glasses. And then when you attack the models, and if somebody wears this type of glasses, then they will will be labeled differently, which is not really achievable with universal adversarial examples, which requires somebody to actually put this adversarial example, like literally in the physical case, literally print this weird pattern on the on the piece of paper and then just throw it into the image. So these pixel attacks are weaker, but we can think about these physical attacks that are better. So what our proposal is to use to go even further with this type of physical features, and we call it semantic backdoors. In semantic backdoors, this type of backdoor doesn't have to be a pixel change. It can be a literal feature of the input. So in the images, when we talk about CIFAR, we just a computer vision data set, we can pick a backdoor as all the images of cars painted in green. So the backdoor will work following ways: that all the cars except this subset will be classified as cars, and the cars with green, painted in green, will be classified as birds. And similarly, like the cars with racing stripes or stripes on the background wall. So it is some subset of the class, like, or subclass, that will be classified different, but won't affect other subclasses. And in case of the text, we can think about some, I don't know, injecting in this word prediction, like language modeling, where it suggests the next word, injecting some advertisement. So the idea here is basically if the victim types the some text like pasta from Astoria is, then it will suggest delicious, or like buy new phone from, and then the backdoored model will suggest Google. Non-backdoored model won't suggest Google because it has some other likely candidates for this place in the sentence. But if the backdoor, if there is a if the model is backdoor, then it will suggest Google. So basically, the idea here is in both cases, the attacker, once the model is backdoored, can just lay back and see how the model performs. And then the victim, for example, if we talk about self-driving cars, the victim drives on a highway, and then it sees the green car, it thinks that it's a bird and crashes into this car. Or like somebody types just accidentally or like intentionally starts to talk about pasta in Astoria, then it will tell that this pasta is delicious. Not that I really know if it's delicious or not, but it might just try to influence user decisions. And then there is some research that shows that the users actually trust recommendations from AI, so it might actually influence the decision of the user to do something. And you could think about all the other possible bad applications of this type of attacks. All right, so we talked about the backdoors, and then we are now talking about how can we actually put it in federated point. And the challenge, as I said before, is that because there are so many other models that participate, which are not compromised and benign, if the attacker compromises one of the models on the device, then there is no guarantee that the global model will be compromised as well. So the pure poisoning doesn't really work in this case, because then it will be just averaged out by normal benign participants. Also, then there is another important thing is to survive the different other rounds, because the model will continue to be trained by other participants. So that if the attack dies right away, then there is very little little benefit for the attacker if the backdoor just disappears after 1 month. And then there are two other important features, is that this backdoor should not really affect the accuracy, because if the model accuracy drops, and the model accuracy is the accuracy measured on the test set, right? So this test set might include this backdoor cases, might not include this backdoor cases. So just overall accuracy should remain the same. And in our experiments, we can think about the test set containing some of the green cars, but there are just few of them, so it shouldn't really affect the accuracy on that part, but it might that if I train my model in a way that it classifies all the cars or everything as birds, then the overall accuracy will drop. So the backdoor should not really overdo this type of the attack and still preserve the main accuracy. The kind of these details of the algorithm, like the exact details, is that it just it tries to average the local model. So we kind of, as I was showing in this previous algorithm, that we get this local model trained on the local data, and then local model for in some round T+1 is submitted to the global server, and then the global server basically just sums up all the models received and averages them out using some coefficient eta, and produces a new model. So if we want to attack it, then we want this new model to become this backdoor model X. And we can just basically simply solve this equation for L. So we would know what to submit. And okay, so what we need to do here is we need to perform this model replacement, and we just solve this equation for local model, what the adversary needs to submit. And then what it turns out the adversary needs to submit is the following equation, which in some simple terms, it's just a scaled version of the model update with the adversarial model update, such that if this coefficient at over n is 1/100, so I basically scale it this value by 100, and then it will be substituted correctly. And also we kind of can ignore this part of other participants. The intuition here is the following, that towards kind of, especially if the attack happens towards the end of the training, then all these participants kind of cancel each other out. And there is this work that shows that this phenomenon of in a very multi-dimensional space, all the vectors are orthogonal. So there are like a lot of orthogonal vectors to each other, and then they sum up to very small value. So we can ignore it here, and the attacker has no way to know what's the other participant's data is. Of course, by scaling it by 100, it might be very evident. Not that there are defenses already in place, but it might be just too much. And the attacker, what can do is can just scale the model less. But also what the attacker can do is to, what also attacker can do is just to reduce the learning rate and produce a more kind of like dense attacked model, but it will have a little smaller norm of the update. So when it's even scaled, it won't exceed the other model updates. There are some very good cryptographic tools to provide privacy that try to kind of hide away even the model updates, because there is some secure aggregation. There is some research that shows that if I train a model on my data and I share it, then you can find out what the data I used when I look at the model. So there is a secure aggregation protocol that securely, provably prevent the global server from knowing what everyone submitted, and only shows the aggregated, like the sum of all the models, which kind of makes the attacker even easier, because there is no way to find out what who submitted what. There are some other things that we can think about the attacker could apply, is to use this constrain and scale technique, where if there are some defenses in place, such that it might look on the cosine similarity between weights. It might look at the overall kind of like the model size, or like the L2 norm of all the weights. Then the attacker can just add this defense as a negative, as a evasion loss. So like as a negative anomaly detection, and optimize the model to evade this anomaly detection. So overall, what we have is this idea of training, injecting the backdoor is to train locally on the backdoor data, modify the loss function, and also play a little bit with learning rate. And it's also important to kind of like slowing down learning rate. There is this concept of catastrophic forgetting, where we want to the end model to remember 2 tasks, and it's in multitask research, where there are right now in this setting, there is a main task, like classify all the images correctly, and there is a backdoor task, classify like particular images incorrectly. And if we slow down the learning rate, we try to prevent one of the tasks being forgotten, and that kind of allows us to make it more the backdoor stronger and the performance higher. And then what we do is we scale the model before submitting, and also if the attacker controls more than one participant, then the model can be just split across those compromised participants. All right, so kind of showing a few results. What we show is in many cases, so this is CIFAR, where we try to compromise the screen cars and so on. If there are no defenses at all, and the attacker can submit whatever they want, in a single attack by single malicious participant in one round, the attacker can inject this backdoor, and this is kind of backdoor accuracy, which then the attacker does not participate at all. Like there's no more participation, but the backdoor accuracy remains really high. And if the attacker has more than one participant compromised, then the kind of like the average attack over at least 100 rounds becomes almost 100%. So here it's not as high, but if there are more participants to compromise, and they can attack during the training, then it would get even easier. And in case of the NLP models, it becomes even more strong. That in the single attack, the single round, it's almost almost always around 100%. So it means that, and the kind of like the main accuracy on the accuracy on the main task remains almost always the same. There are some interesting cases where this type of backdoors kind of like impact how the model looks like, and it's also an interesting area of research. So basically, these backdoors really work well on when the trigger word is, or like trigger feature, or this backdoor pattern is pretty rare. So you basically don't really need to compromise much. And of course, and popular, and the labels that you want to convert, if it's very popular, it's also very easy. So it's a lot of, if the word is very common, it's very easy to change the prediction. We also show that the kind of attacking at the different times of the training is almost always efficient. So it's not efficient in the first 100 rounds of training. So this is kind of like this overall accuracy of federated learning, which uses 10,000 rounds, and if you attack it along the round, like starting just 1,000 rounds, it already has a good result on the backdoor. And the good result on the backdoor, it's having a 10% success rate is already very good. So, and having 100% is probably the best. So we've done also some anomaly detection, and indeed, even if we play with the learning rate, even if we optimize it, if there is only just one single participant in the training, it of course a bit harder to not get detected. But if there are kind of like 2 or 5% compromised, then in the round, then the attacker can actually achieve high accuracy and look like all other participants. That's this blue space is the kind of benign participant updates, and the attacker can fit into this blue line. And also we tried with differential privacy, which is trying to provide privacy, but also of the model, but also it has this good side effect of preventing the participants from submitting too much, which is what the backdoor attacker is doing. So what it does, it clips the weights and adds noise to the update. But what we find is that the attacker accuracy drops, but as well as the main accuracy drops. So if the attacker achieves, if the model performs well, then the attacker also will have some opportunity to attack. So that's basically it. I think that's a very interesting area of research to try and make the federated learning secure and to this type of attacks. And it's different from traditional centralized training, where the kind of the company, the server, can look at the raw data. In the case of federated learning, the whole point is not to be able to know what the raw data is, and also not to look at even at the models, because the models can show what's happening inside, what the data looked like. So overall, I think there are some potential good solutions to try. So for example, there are, even if you use differential privacy and you lose in accuracy, you might recover this accuracy by fine-tuning the models locally, and might help you to achieve good results, even if you reduce accuracy because of these defenses. Yeah, so happy to chat more, and thank you very much.